Here we are at part 2 for chapter 22, the chi-square goodness of fit test. Well, here's an M&M's example. According to the Mars Candy Company, 13% of plain M&M's in a large bag should be brown, 14% should be yellow, 13% red, 24% blue, 20% orange, and 16% green. We want to know whether a randomly selected large bag of plain M&M's has contents that follow this distribution. So we count the number of M&M's of each color and obtain the results below in the following table. And we want to do a this goodness of fit test at a 0.01 significance level. So when we open up the bag, we saw that we have 61 brown, 64 yellow, 54 red, 61 blue, 96 orange, and 64 green. And we want to make sure that that's following the distribution that the Mars Candy Company wants to have for a large bag of M&M's. So the first row is the actual counts that we got from the bag. Now let's look at the expected numbers. Now, the total number of M&M's in that bag, there were 400 M&M's. So if 13% of those should have been brown, we should have seen 52 brown, but we really saw 61. We should have seen 56 yellow, because 14% of 400 should have been yellow. That would have been 56. So we saw 56 instead of 64. 13% should have been red. We had 400 times 13%. We should have seen 52, but when in the actual count there were 54. 24% of the 400 should have been blue. So we should have seen 96. However, we only saw 61. For the orange, 20% of the 400 should have been orange, according to what Mars would like. And so we should have seen 80. We saw 96. For the green, 16% we should see in a bag of M&M's. Well, 400 times 0.16 is 64. We should have seen 64, and we did. So that one was right on the money. So now, to start to find our test statistic, we have to take each of the categories and do the observed minus the expected, square that value, and divide it by the expected. So I'm going to take 61 minus 52, square that value, and divide by 52. When I do that, I get 1.558. When I take 64 minus 56, square that value, divide by 56, that's where I get 1.143. And so forth, to get all the numbers down below. When I do that, and I total that row, that's my test statistic. The test statistic is 18.738. So to do my peak value calculation, I go into Minitab, I put CDF 18.738 K1. The subcommand is chi-square with 5 degrees of freedom because we have 6 categories. Degrees of freedom is 6 minus 1 or 5, and then the rest of the command, so we get that our p-value is 0.002. And if you notice on the first line, I added the MTB prompt. Somehow that got cut off, so that so that you could see the command you would use in Minitab to find that p-value. Since that p-value is less than alpha, we reject the null hypothesis. So our conclusion is, at 0.01 level of significance, there's sufficient evidence to reject the color distribution advertised by the Mars Candy Company, or that there's sufficient evidence to conclude that the color distribution is different than advertised. Either one of those will do for our interpretation of this problem. So the summary for the goodness of fit test is that the goodness of fit test applies to a situation where there are a series of independent trials and each trial has 3 or more possible outcomes. The test statistic to be used combines all outcomes and all the expected counts. The test statistic has approximately a chi-square distribution when the null hypothesis is true. So our null hypothesis looks something like this, and the alternative is just the proportions are not as specified in that null. For a sample of n subjects, observe how many subjects fall into each category. Calculate the expected number of subjects in each category under the null hypothesis. Remember that expected count is just n times pi for the ith category. This is our formula for the chi-square test, remember that weird little e is the summation. We're summing each of those different categories. The observed count minus the expected count squared divided by the expected count. We do that for each category, and then we add those up. The degrees of freedom for the statistic are k minus 1, the number of categories, minus 1, and we find our p-value. We're going to use Minitab. So we'll change that to finding that p-value using Minitab. So let's take another example. So looking at this example, it says a random sample of 140 births from the local records was collected to show that there are fewer births on Saturday and Sundays than there are on weekdays. That's what they're trying to prove. So what they did is they got the actual births on each of these days, and they're saying that this data gives significant evidence that local births are not equally likely on all the days of the week. So if I had 700 births, I would think if they're equally likely that 100 births on each day would occur. So let's see how we would do this. We're looking at 140 births. We've got 7 days each week. We would assume that there should be 20 births each day. So our null hypothesis would say that P1, P2, P3, P4 for all the days of the week is 1 and 7 for each of the days. So, as you can see, n, which is 140 times 1 and 7, that's 20. That's how we get these expected numbers of births for each of the categories, since the probabilities are all the same for each day of the week. That's what we're assuming. So we take those observed counts minus 20, square that value, and divide it by 20. We do it for all 7 days of the week, and we get our test statistic of 7.60. Make sure you can do it and that you can get 7.60. Using Minitab, we can find the p-value. The things that we need are the test statistic and the degrees of freedom. We have 7 categories, therefore our degrees of freedom is 6. Our test statistic is 7.60, so we use our little algorithm, put it in Minitab, and we find that our p-value is 0.27. 0.27 is greater than our alpha, so we fail to reject the null hypothesis. So there is insufficient evidence to support the claim that there are fewer births on Saturdays and Sundays than there are on the weekdays. And that is chi-square tests. And this is the last slide for the semester. I wish you all very, very good luck on the final, and I thank you very much for a wonderful semester.